Good afternoon, Year 12. Just wanted to go through this quick example to help you with the work on the worksheet today. Okay, so this is the question on screen that the example will help you with. Instead of looking at just one step in the C&O process, we're going to have a look at the net effect. Now, when we have a look at the overall reaction or the net effect for the C&O cycle, it's actually the same reaction overall as for the proton-proton chain. We've got 4 hydrogen nuclei fused together to form one helium nuclei. We describe that as a helium-4 nucleus containing two protons, 2 neutrons, and then in order to account for the extra positive charge, we have to have two positrons, and there's also 2 of those electron neutrinos produced that we saw yesterday. So writing the nuclear equation, we just write down everything that's present. So it looks like this. So we've got each of the things present. We've got first our hydrogen, helium, then we've got our positron, and then our electron neutrinos. Now, if we have a look, there's also some numbers included in this equation. There's a number out the front, a coefficient, if we've got multiple of one thing. For example, we've got 4 hydrogens. Then we've also got two numbers listed one on top of each other. Now, the number up the top tells you how many protons plus neutrons there are in that atom, while the number down the bottom tells us the charge. So for hydrogen, there's 1 proton, so it's a positive charge of 1. Helium, 2 protons, positive charge of 2. Whereas the positron, each of those positrons has a positive charge of 1, but it doesn't contain a proton or a neutron. So there's a 0 up the top. If we were to put zeros in front of the electron neutrino, we'd put 0 up the top, 0 up down the bottom. No, we don't really need to do that. Okay, here we go. We'll start doing the calculations. Now we want to do first a calculation for mass defect. Now on your worksheet you've got some values for what an atomic mass unit is. You can also find those values on your data sheet, and because the data sheet values are slightly different, they're the ones I'm going to be using in my calculation. Okay, now to the right here we've got the mass of each of the things that we've got in our equation in atomic mass units. Might notice that the electron neutrino is not mentioned. That's because it's got a mass of 0. So we'll just ignore that. Okay, so mass defect, we need to have a look at the mass before, our 4 hydrogens, and then our mass after. So that's our 2 positrons and our helium. Now for mass defect, we go the initial mass minus the final mass. Put that into your calculator. You get this answer in atomic mass units here. Now we could also express our mass defect in kilograms, and we're just going to use the conversion factor that we see up here. Okay, so doing that in kilograms, that's our mass defect. Right, finally, once we've got our mass defect, we can calculate the amount of energy that's released by a nuclear reaction. So there's actually a bit of a trick to doing this quickly if we've got something in atomic mass units. Okay, so to calculate the energy in mega electron volts, we can just simply multiply by the number of atomic mass units that we've got present by this conversion factor here. So it's 931.5 mega electron volts per c squared. Now this conversion factor gives us our energy released in mega electron volts. Because if you notice when you just do E equals mc squared, the c squared is going to cancel with the per c squared. And so we can just multiply the two underlined numbers together to give the energy released. Alternatively, we can also express our energy released in joules. Now one way of doing that is to use our values for c squared and m that we got in kilograms. Get an answer like that. Another way is to convert from mega electron volts into joules, and to do that we would multiply our value in mega electron volts times by 10 to the 6 for our conversion back down into electron volts, times by our expression for the conversion between joules and electron volts. So this is how many joules there are in an electron volt. So we could get this same number down here using that method. Okay, either of those is fine. Have a good day.